So in this session, we're going to talk more about solutions. Some of this should be review as we discuss solutions in an earlier chapter, but to review, a solution is a homogeneous mixture, so that means it's smooth and consistent, of two or more substances. Those substances include a solvent and solute. The solvent is the majority component, the solute is the minority component that gets dissolved. When a solution has water as the solvent, it's called aqueous, and it can have solid, liquid, or gas as the solute, can be dissolved in water. First, we'll talk about solutions in a qualitative sense, where solubility of a substance is the amount of substance that dissolves in a given amount of solvent, and it can depend on the intermolecular forces that we just learned about, where the main thing to remember is the idea that like dissolves like. So a polar solvent can dissolve polar solutes, and it can also dissolve ionic solutes using ion dipole forces. A nonpolar solvent can only dissolve nonpolar solutes. When we're talking about trying to mix solvents together, the words we would use would be miscible, which sounds a lot like mixable and means the same thing, that solvents can mix together because they're similar, or it can be immiscible. That's when solvents are not mixable, that they do not mix together. So solvents that are similar, like water and alcohol, would be miscible, that they do mix together, whereas solvents that are different, like oil and water, would be immiscible, that they do not mix together. I'm going to go ahead and show a quick example of how you can look at solubility in this qualitative sense. So here we have some examples of different vitamins, and we're trying to determine if they are fat soluble or water soluble. So fat is nonpolar, so any of these molecules that are mostly nonpolar will be fat soluble, and water is polar, so any of these vitamins that have polar components will be water soluble. So here we would look at each molecule and look for things that are polar that would be attracted to the water. So vitamin C has multiple OH groups on there, and all of those can hydrogen bond with the water molecules. So this would be water soluble. Here in this vitamin, we see a couple of groups that have oxygens that are polar, but they're on opposite sides of each other and mostly opposing each other, so they kind of cancel each other out. So overall, this molecule would be nonpolar, which would make it fat soluble. Here we have another vitamin where we have this big bulky part that is all nonpolar because it's just carbon and hydrogen. And we have this one little polar thing on the end that can hydrogen bond with the water. But overall, this molecule has a lot more that is nonpolar. So this is going to be slightly soluble in water because of the OH group, but mostly it will be fat soluble. And then here we have our last example of a vitamin. We're again highlighted, we have multiple groups that are polar and that can hydrogen bond with the water. So this has a lot of places where the water can attach to it or be attracted to it, making this vitamin mostly water soluble. So for a little more practice, this asks whether each compound is soluble in hexane. Now we've not learned organic naming at all in this class, but hexane is an organic compound that only has carbon and hydrogen. Because it only has carbon and hydrogen, and since it's hexane, it would have 6 carbons. Since it's all carbon and hydrogen, this would be a nonpolar solvent. So in order for it to be soluble in something that's nonpolar, we're looking for compounds that are nonpolar. So our first option, water, we know that water is polar because of the lone pairs on the oxygen. So water would not be soluble in hexane. Here we have another example of something that is only carbon and hydrogen. So this is very similar to hexane. So this would also be nonpolar. So it would be soluble in hexane. Ammonia has a lone pair on the nitrogens. So this would be polar, so that would not be similar to hexane. So ammonia would not be soluble. And then here, hydrogen chloride, since it's not in water, that's why we're not naming it like an acid, would also be polar because the hydrogen and chlorine have different electronegativity values. So since this is a polar compound, it would not be soluble in hexane. So of these compounds, the only one that is soluble in hexane would be the propane because it is the most similar to the hexane because they are both nonpolar. When we're considering solution formation, there's a couple different things at work. These are all things that you'll learn more about if you decide to continue and take general chemistry too. Solution formation is the tendency towards greater entropy. That entropy can be thought of like chaos or disorder as particles tend to disperse, and that can cause solutions to form. But part of the reason the intermolecular forces matter is basically the solute and solvent have to like each other and have attractions to each other more than they're attracted to themselves. It's kind of like your junior high dance where the girls and boys are on the opposite sides of the room, and it's not until they start to like each other that they're willing to mix together and mingle. Another thing that to keep in mind for solution formations, and this is also related to phase changes as well, is it's something called a dynamic equilibrium, where dynamic means that things are still moving, that this doesn't just mix and then stop and nothing happens. Equilibrium means that things level out. It doesn't mean that they're equal, it just means that they level out and the overall concentration stops changing. So some important terms to know for this are saturated, unsaturated, and supersaturated. Saturated means that you have the maximum amount of solute dissolved in your solution. Unsaturated means you have less than the equilibrium amount of solute dissolved in your solution. Supersaturated is unstable because it has more of the solute dissolved than it normally would be able to. Supersaturated solutions usually involve some kind of trickery where you make some kind of change to the solution to get it to dissolve extra solute and then slowly adjust it back to the normal conditions where the solute manages to stay in the solution even though there isn't quite room for it. So that's why these are unstable, is that extra solute can come out of the solution very easily. Some qualitative trends that are important for this chapter is to know that the solubility of most solids in water will increase as you increase the temperature. This means if you make a solution warmer, you can get more solute to dissolve if it's solid. For gases, it's the opposite. If you heat up a solution that has a gas solute, those gas bubbles will get more energy and try to escape the solution. This can be observed when you think of soda, where if you leave your soda out where it's warm, it goes flat a lot faster than if you keep it in the refrigerator where it's cold. Another important trend for gases has to do with pressure, that you can also increase the solubility of a gas by increasing the pressure outside the solution. This is why your soda is kept under pressure, and you can hear that pressure being released when you open your soda. The next part of this deals with concentration. This is a property of a solution that expresses the amount of solute compared to the solvent in a solution. Some qualitative terms that we've already discussed would be a dilute solution, which has a relatively small amount of solute dissolved, versus a concentrated solution that has a relatively large amount of solute dissolved. We already did a little bit talking about dilution calculations, but if you peek ahead a little, I did review that equation that you can use for when you're doing dilutions, where we can look at the concentration, starting concentration times the starting volume will equal the ending concentration times the ending volume. We've already explored some of the units for molarity, or for concentration, including molarity and mass percent. But this table shows a lot of other options that we have for looking at solution concentration. So molarity is certainly one that we use a lot in chemistry, but these are some other important units that we can use for concentration as well. And we'll do some examples in a moment of how to calculate each of these types of concentration and also how to convert between them. One thing that you definitely want to notice is that most concentrations, the bottom unit involves the entire solution. That molarity is based on the volume of the entire solution in liters, and all of these other ones below molality are based on the total amount of the solution on the bottom. Molality is special because it is based on the mass of just the solvent in kilograms on the bottom part of your equation. So that is an important thing to keep in mind, that this is something that is special about molality, and this is a type of concentration that we'll be using in some calculations in the next session. On the bottom of this overview, it has some things that are important to review from previous chapters, because these concepts are concepts that we'll be continuing to use as we do problem solving and conversions in this chapter. So now we can go ahead and do some examples where we calculate all these different types of concentrations. So first I have some examples where the work is already done. I'm just showing you an example of how to calculate all of these different types of concentration based off different information that's given. So molarity, so you want to make sure we know all these definitions. Molarity is the moles of the solute divided by the volume of the solution in liters. So based on what's given in the problem, we're not given the moles of the solute, but we are given the grams. So we convert the grams of solute into moles so that we can put that part on top. And then we are given the volume of the solution, but in milliliters. So that's why they went ahead and converted our milliliters, that it was 515 milliliters, and they went ahead and converted that. 1 liter goes with 1,000 milliliters. And that's how they were able to get the molarity. Molality still has the same moles of solute on top, so we don't need to recalculate that. This time it's divided by the mass of the solvent in kilograms, and that part was given, so we didn't need to do any conversions there. And so that's how we're able to get the molality. So again, this kind of fancy looking italic M is molality. You could call that mole, whereas the big M is called molar, like the tooth. So again, just a subtle difference that you want to make sure you're paying attention to. Here we have an example calculating mass percent. In this case, the mass of the solute was given, so we want to make sure you know this definition. So the mass of the solute was given. On the bottom, to get the mass of the entire solution, they have the mass of the solute plus this is the mass of the solvent, because they told us how much the water weighed. They did not tell us how much the whole solution weighed. So that's why we have to add solute plus solvent, and you may need to include parentheses to make sure that all of that stays on the bottom to give your mass percent. Then we asked for mole fraction, so that's where we take the moles of the solute. So here's another definition you need to have memorized, divided by the total moles on the bottom, so solute and solvent. So we had calculated our moles of solute in the beginning that we calculated in part A. And then we have to convert our moles, our mass of water, sorry, this is what was given. So we convert that to moles so that we have the moles of the solvent, because water is our solvent. And for mole fraction, there are no units, because your mole units all cancel out when you divide. If we did mole percent, we would just multiply that by 100. which they show here. So they took the mole fraction that we just calculated, multiply it by 100 because percent means per 100, and that's how you have mole percent. So we can get into some calculations for this example. Zoom in a little bit. So molarity, we know we need the moles of the solute per liter solution. So we are not given the moles of the solute. We do need to go ahead and identify that sucrose is our solute. That's the stuff that's getting dissolved in this much water. So water is our solvent. So identifying those can definitely be helpful. So we're not given the moles, but we are given the mass of the solute. So we know how to convert that. 50.4 grams of our sucrose, C12H22O11, times 1 mole of that. We would add up all the masses from the periodic table. Comes to 342.34 grams. So there your grams cancel, and we have 0.147 moles. So this is our solute. To get molarity, we need to divide by the liters of solution. So we were given the milliliters, so we have 355 milliliters. So we can multiply that by 1 liter, goes with 1,000 milliliters. So the milliliters cancel, and we have 0.355 liters. So now we can go ahead and plug in for our molarity. So we have our moles of the solute divided by our liters of the solution. It's 0.415 molar. Gives us our molarity. That was part A. Molality, then we'll go down here. So molality means we need the moles of the solute, we already calculated, divided by the kilograms of solvent. So molality is the only one that's based on solvent. So we already calculated our moles. So we already have our top part, 0.147 moles of solute on top. And we need to divide that by the kilograms of solvent, which was not given directly. Oh yeah, it is 0.332 kilograms of water, so that was given. We don't even need to calculate that. Because water is our solvent. So that gives us 0.443, and this is where I try to make that M look a little extra fancy because it's for molality. So you don't want to confuse it with molarity or moles or mass or meters or any of that. So that's why we try to make the M look a little extra fancy. Now in this case, these two values are very, very similar, that they're both around 0.4. That will not always be true. That it is actually possible to have a molality that's much bigger than your molarity, since it is based on just the solvent instead of the whole solution. So they won't always be so similar. They just happen to be similar in this situation. We'll go over here for our mass percent. So mass percent, so we're looking for part C now, is the mass of the solute divided by the total mass of the solution times 100%. So the mass of the solute, again, is given 50.4 grams of sucrose is our solute. The mass of the entire solution is not given. We are given the volume of the entire solution. So if we knew the density of the solution, we could find the total mass that way. But we are given the mass of the solute and the mass of the solvent. So we can actually add those. We just have to make sure our units match to figure out the mass of the solution. So we've got 50.4 grams of our solute plus, and we have to make our units match, so we can convert this is the same as 332 grams of water. So that's our solvent. So if we add the solute and the solvent, that equals the whole solution times 100%. So that gives us a mass percent of 13.2. That was for part C. And then part D was to get the mole fraction. So the mole fraction is where you have the moles of the solute, which we already calculated, divided by the total moles, which we do not know the total moles yet. So the moles of solute we already calculated. Pardon me for 1 second. Better link, so hopefully that'll take care of it. We already calculated the moles of the solute, but we still need to find our total moles. So the piece that we're missing for our total moles is to know the moles of the solute. So we have, or of the solvent, sorry. So we have 322 grams of solvent. That was water. So to convert that to moles, we know that 1 mole of water goes with about 18 grams. So that tells us that our moles of water is 18.4 moles. This is for our solvent. So to get our mole fraction then, we had our moles of solute was 0.147 moles of solute divided by our total moles. So we'll add the 18.4 moles of solvent plus our moles of solute. So we'll have 18.57 moles total on the bottom. So that way our mole fraction, sorry for writing over this guy, is 0.00793, and there's no units for mole fraction. And then E asked for mole percent, so we just take that mole fraction times 100%, so that would be 0.793% based on the moles. Now we can also use concentration as a way to convert, very similar to how we've used density as a way to convert. We've used mass percent as a way to convert already. We've used molarity as a way to convert. Anything that has units on the top that are different than the units on the bottom can be used as a conversion between those units. So in this example, we're trying to find the volume in milliliters of a soft drink, and we're given 10.5% sucrose or sugar and has this much mass, 78.5 grams of sucrose. We're also given the density of the solution. So this means, since it's of the solution, this means that 1.04 grams of solution goes with 1 milliliter of solution. So this is a way that you can convert between the mass of the solution and the volume of the solution. So we're trying to find the volume of the solution. We know how to find the volume of solution if we can find the mass of solution, because we have a way to connect those. And we can find the mass of the solution if we know the mass of the solute using our mass percent. And down here they show you, so we had 10.5% sucrose, and percent means per 100, so that's the same as 10.5 grams sucrose goes with 100 grams solution. So that's where they used that as a conversion factor here so that they could cancel out grams of sucrose that they're given in order to get the grams of solution. And then we can use the density to cancel out the grams of solution in order to get milliliters of solution. So these conversions, you're going to want to make sure you're very careful labeling your units, that not all gram units are the same. So it's helpful to write a little bit extra so that you can differentiate between the mass of the solute and the mass of the solution. So here we have our final answer. It's a good idea to go ahead and make sure that this makes sense, that we're trying to get 78.5 grams of sucrose, and we know that we're about 10%, 10.5% in our solution. So it makes sense that we would need a lot more of our solution, because about 10% of the solution, it's not exactly equal to our mass, but it's at least in the same ballpark. So that at least gives us a rough idea that we went the right way, that we didn't accidentally multiply when we were supposed to divide, or vice versa. Here we have a similar example. So here this time our goal is to find out what mass of sucrose in grams, so here's our goal, is contained in 355 milliliters. So this is volume, because milliliters are volume units, of a soft drink that is 11.5% sucrose. And percent is almost always going to be by mass. So if it doesn't specify, and assume that it's mass. So here we have mass percent. So this 11.5% is the same as saying 11.5 grams of sucrose per 100 grams solution, because percent means per 100. We're also given a density that this is for the solution. So this means that 1.04 grams of solution, not sucrose, solution, is equal to 1 milliliter of solution. And so to develop our plan, this is where we start to look at how our units connect. So we have something with milliliter units for the solution, and we know how to go from milliliters of solution to grams of solution. And then once we have grams of solution, we can use that to turn it into grams of sucrose. So here's our plan, is to go milliliters solution to grams solution using density. And then we can go from grams of solution to grams of solute, in this case sucrose, using our percentage. So we have our plan. So we can take our 355 milliliters of solution. And so we need milliliters on the bottom and grams solution on top. So our density showed us that 1 milliliter goes with 1.4 grams. So that lets us cancel our volume units. And then to get our grams solute, we know that we have gram solution, 100 gram solution has 11.5 grams of our solute. So that lets us cancel gram solution. And then we can plug in to get 42.5 grams of solute. Our solute was sucrose. So notice for this, we actually did not need to use the periodic table or the molar mass at all. A lot of times they see students just trying to use it for every single one, but it's not always necessary. You have to look at your goal units and look at your starting units and find a way to connect them. The next couple examples involve converting between different kinds of units. And for these, I definitely recommend breaking the units up into two different conversion problems. So I recommend converting the top units and converting the bottom units and then plugging them back in to your definition. So in this example, we're trying to find what is molarity. So that's our goal unit, is to find molarity. So we know we need moles and we know we need liters. And then we look at what we're given. Well, we're given a percent. So this is 6.56 grams of our glucose divided by 100 grams of our solution. So that's where we can start to make a plan of how can we make our starting top units get to our ending top units, and how can you make your starting bottom units get to your ending bottom units. So that's where we take this into two different paths. So on top, we want to turn our grams of solute into moles of solute, and that's what we need for the top part of our molarity. And then on the bottom, we can take our grams of solution, use the density to find the volume, and then convert those volumes into liters, because molarity is always going to be based on liters. And so then they show your work where we convert the grams of solute into moles of solute. And then they convert the mass of the solution into volume of solution. And then we can plug that in. The moles of the solute divided by the liters of the solution gives you the molarity. So if you're trying to memorize this step by step, it's going to be a lot harder than if you just learn how to use those problem-solving strategies that we've been using all semester, of looking at how can you turn the starting units into the goal units that you're trying to get. So this first one's very similar to the one we just did, where we're trying to find molarity. So molarity, we know we need moles solute divided by liters solution. So we look at the information we have to see how we can get that. So we have 10.5 grams of our glucose, C6H12O6, per 100 grams of our solution. So on top, we need to turn these grams into moles. So we have 1 mole of our solute. And this is where we will use the periodic table to add up all those masses. Comes to 100 grams. So those grams cancel. And we get moles. Oh, oops, that's not the right mass. 180.2, we'll say. Oh, sorry about that, I was looking at the wrong thing. So 0.058275. We can keep a couple extra digits right now. We don't want to round too soon. So there's our moles of our solute. So that's what we need for the top part of our molarity. On the bottom, we need to find the liters of solution. Right now we have the grams of solution. So we can use the density to turn our grams of solution. We need to get to volume. So our density is 1.03 grams, goes with 1 milliliter. So that lets our gram solution cancel and gives us 97.087. Again, keeping a couple extra digits, milliliters. But molarity has to be per liter, not per milliliter. So we can go ahead and move our decimal. Go ahead and round a little bit now. Liters of our solution. And now we can go ahead and calculate molarity. So the molarity is our moles divided by our liters. It's 0.6, and that we actually had 3 sig figs the whole way, so we keep those last 2 zeros are significant. We don't just want to say 0.6. We put 0.600 to show 3 significant figures, because the front 0 is placeholder, it's not significant. So this next example looks exactly the same, but there is one letter difference, because we're looking for molality instead of molarity. So for molality, we need the moles solute, which we already calculated, divided by the liter or the kilograms of solvent of our water. Yes, it does not specify that it is aqueous, so you can assume that it is aqueous unless it says otherwise, though it doesn't actually matter right now whether or not it's water, because we can actually find this kilogram solvent because we know the mass of the solution is 100 grams, and we need to know the mass of the solvent, so we can subtract the mass of the solute that was given, 10.5, so 100 minus our 10.5 is 89.5 grams of solvent, and we need to turn that into kilograms. So to get molality, we have the moles of solute that we calculated in the last problem, divided by the kilograms of the solvent. So we have to convert that to kilograms. That would be 0.0895 kilograms of solvent, because molality is the only one that is just based on solvent, not the whole solution. And so that comes to 0.1. And then again, we try to make that fancy looking M for our molality units. So hopefully those examples were helpful to see how to calculate different types of concentration, how to use different types of concentration in conversions, and then how to use problem-solving skills to convert between one type of concentration and another. And just remember to focus on those goal units that they're asking for and interpret all the other information that you have available so that you can use that information to get your goal units.